Caesium is the chemical element with the symbol Cs and atomic number 55. It is a soft silvery gold alkali metal with a melting point of 28 degrees Celsius or 83 degrees Fahrenheit, which makes it one of the only 5 metals that are liquid at or near room temperature. Caesium has physical and chemical properties similar to those of rubidium and potassium. The metal is extremely reactive and pyrophoric, reacting with water even at minus 116 degrees Celsius or minus 177 degrees Fahrenheit. It is the least electronegative element that has stable isotopes, of which it has only one, Caesium-133. Caesium is mined mostly from pollucite, while the radioisotopes, especially Caesium-137, are extracted from waste produced by nuclear reactors. Two German chemists, Robert Bunsen and Gustav Kirchhoff, discovered caesium in 1860 by the newly developed method of flame spectroscopy. The first small-scale applications for caesium have been as a getter in vacuum tubes and in photoelectric cells. In 1967, a specific frequency from the emission spectrum of Caesium-133 was chosen to be used in the definition of the second by the International System of Units. Since then, caesium has been widely used in atomic clocks. Since the 1990s, the largest application of the element has been as caesium formate for drilling fluids. It has a range of applications in the production of electricity, in electronics, and in chemistry. The radioactive isotope Caesium-137 has a half-life of about 30 years and is used in medical applications, industrial gauges, and hydrology. Although the element is only mildly toxic, it is a hazardous material as a metal, and its radioisotopes present a high health risk in case of radiation leaks. Section 1. Characteristics. Physical properties. Caesium is a very soft, it has the lowest Mohs hardness of all elements, very ductile, silvery white metal, which develops a silvery gold hue in the presence of trace amounts of oxygen. It has a melting point of 28.4 degrees Celsius or 83.1 degrees Fahrenheit, making it one of the few metals that are liquid near room temperature. Mercury is the only metal with a known melting point lower than caesium. In addition, the metal has a rather low boiling point, 641 degrees Celsius, or 1,186 degrees Fahrenheit, the second lowest of all metals. Its compounds burn with a blue color. Caesium forms alloys with the other alkali metals, as well as with gold, and amalgams with mercury. At temperatures below 650 degrees Celsius, or 1,202 degrees Fahrenheit, it alloys with cobalt, iron, molybdenum, nickel, platinum, tantalum, or tungsten. It forms well-defined intermetallic compounds with antimony, gallium, indium, and thorium, which are photosensitive. It mixes with the other alkali metals, except with lithium, and the alloy with a molar distribution of 41% caesium, 47% potassium, and 12% sodium has the lowest melting point of any known metal alloy, at minus 78 degrees Celsius, or minus 108 degrees Fahrenheit. A few amalgams have been studied. CSHG2 is black with a purple metallic luster, while CSHG is golden colored, also with a metallic luster. Chemical properties. Caesium metal is highly reactive and is very pyrophoric. In addition to igniting spontaneously in air, it reacts explosively with water even at low temperatures, more so than other members of the first group of the periodic table. The reaction with solid water occurs at temperatures as low as minus 116 degrees Celsius, or minus 177 degrees Fahrenheit. Because of its high reactivity, the metal is classified as a hazardous material. It is stored and shipped in dry, saturated hydrocarbons, such as mineral oil. Similarly, it must be handled under inert atmosphere, such as argon or nitrogen. It can be stored in vacuum-sealed borosilicate glass ampules. In quantities of more than about 100 grams, or 3.5 ounces, caesium is shipped in hermetically sealed stainless steel containers. The chemistry of caesium is not very similar to that of other alkali metals, but is more closely similar to that of rubidium, the element above caesium in the periodic table. Some small differences arise from the fact that it has a higher atomic mass and is more electropositive than other non-radioactive alkali metals. Caesium is the most electropositive stable chemical element. Compounds. The vast majority of caesium compounds contain the element as the cation Cs+, which binds ionically to a wide variety of anions. One noteworthy exception is provided by the C-side anion Cs-. Other exceptions include the several suboxides. Returning to more normal compounds, salts of Cs+ are almost invariably colorless unless the anion itself is colored. Many of the simple salts are hygroscopic, but less so than the corresponding salts of the lighter alkali metals. The acetate, carbonate, halides, oxide, nitrate, and sulfate salts are water-soluble. Double salts are often less soluble, and the low solubility of cesium aluminum sulfate is exploited in the purification of Cs+ from its ores. The double salt with antimony, such as CsSbCl4, bismuth, cadmium, copper, iron, and lead, are also poorly soluble. Cesium hydroxide, CsOH, is hygroscopic and a very strong base. It rapidly etches the surface of semiconductors such as silicon. CsOH has been previously regarded by chemists as the strongest base, reflecting the relatively weak attraction between the large Cs+ ion and OH-. Many compounds are far more basic than CsOH, such as N-butyllithium and sodium amide. Complexes. Like all metal cations, Cs+ forms complexes with Lewis bases in solution. Because of its large size, Cs+ usually adopts coordination numbers greater than 6 coordination, which is typical for the lighter alkali metal cations. This trend is already apparent by the 8 coordination in CsCl versus the halite motif adopted by the other alkali metal chlorides. Its high coordination number and softness, tendency to form covalent bonds, are the basis of the separation of Cs+ from other cations, as is practiced in the remediation of nuclear wastes, where 137Cs+ is separated from large amounts of non-radioactive K+. Halides. Cesium chloride, CsCl, crystallizes in the simple cubic crystal system. Also called the cesium chloride structure, this structural motif is composed of a primitive cubic lattice with a 2-atom basis, each with an 8-fold coordination. The chloride atoms lie upon the lattice points at the edges of the cube, while the cesium atoms lie in the holes in the center of the cubes. This structure is shared with CsBr and CsI, and many other compounds that do not contain Cs. In contrast, most other alkaline halides adopt the sodium chloride NaCl structure. The CsCl structure is preferred because Cs+ has an ionic radius of 174 picometers and Cl- 181 picometers. Oxides. More so than the other alkali metals, cesium forms numerous binary compounds with oxygen. When cesium burns in air, the superoxide CsO2 is the main product. The normal cesium oxide, Cs2O, forms yellow-orange hexagonal crystals and is the only oxide of the anti-CdCl2 type. It vaporizes at 250 degrees Celsius, or 482 degrees Fahrenheit, and decomposes to cesium metal and the peroxide Cs2O2 at temperatures above 400 degrees Celsius, or 752 degrees Fahrenheit. Aside from the superoxide and the ozonide CsO3, several brightly colored suboxides have also been studied. These include CS7O, CS4O, CS11O3, CS3O, dark green, CSO, CS3O2, as well as CS7O2. The latter may be heated under vacuum to generate CS2O. Binary compounds with sulfur, selenium, and tellurium also exist. Isotopes. Cesium has a total of 39 known isotopes that range in their mass number, i.e. number of nucleons in its nucleus, from 112 to 151. Several of these are synthesized from lighter elements by the slow neutron capture process, S process, inside old stars, as well as inside supernova explosions, R process. However, the only stable isotope is 133Cs, which has 78 neutrons. Although it has a large nuclear spin, 7.2+, nuclear magnetic resonance studies can be done with this isotope at a resonating frequency of 11.7 MHz. The radioactive 135Cs has a very long half-life of about 2.3 million years, while 137Cs and 134Cs have half-lives of 30 and 2 years, respectively. 137Cs decomposes to a short-lived 137 MBa by beta decay, and then to non-radioactive barium, while 134Cs transforms into 134Ba directly. The isotopes with mass numbers of 129, 131, 132, and 136 have half-times between a day and 2 weeks, while most of the other isotopes have half-lives from a few seconds to fractions of a second. There are at least 21 metastable nuclear isomers. Other than 134MCs, with a half-life of just under 3 hours, all are very unstable and decay with half-lives of a few minutes or less. The isotope 135Cs is one of medium-lived fission products of uranium, which form in nuclear reactors. However, its fission product yield is reduced in most reactors because its predecessor, 135Xe, is an extremely potent neutron poison and transmutes frequently to stable 136Xe before it can decay to 135Cs. Because of its beta decay to 137MBa, 137Cs is a strong emitter of gamma radiation. Its half-life makes it the principal long-lived fission product, along with 90Sr. Both are responsible for radioactivity of spent nuclear fuel after several years of cooling up to several hundred years after use. For example, 137Cs together with 90Sr currently generate the largest source of radioactivity generated in the area around the Chernobyl disaster. It is not feasible to dispose of 137Cs through neutron capture due to the low capture rate, and as a result, it must be allowed to decay. Almost all cesium produced from nuclear fission comes from beta decay of originally more neutron-rich fission products, passing through various isotopes of iodine and xenon. Because iodine and xenon are volatile and can diffuse through nuclear fuel or air, radioactive cesium is often created far from the original site of fission. With the commencement of nuclear weapons testing around 1945, 137Cs was released into the atmosphere and then returned to the surface of the Earth as a component of radioactive fallout. Occurrence. Cesium is a relatively rare element, as it is estimated to average approximately 3 parts per million in the Earth's crust. This makes it the 45th most abundant of all elements and the 36th of all metals. Nevertheless, it is more abundant than such elements as antimony, cadmium, tin, and tungsten, and 2 orders of magnitude more abundant than mercury or silver, but 30 times less abundant than rubidium, with which it is so closely chemically associated. Due of its large ionic radius, cesium is one of the incompatible elements. During magma crystallization, cesium was concentrated in the liquid phase and crystallizes last. Therefore, the largest deposits of cesium are zone pegmatite ore bodies formed by this enrichment process. Because cesium does not substitute for potassium as readily as does rubidium, the alkali evaporite minerals sylvite, KCl, and carnallite, KMgCl3-6H2O, may contain only 0.002% cesium. Consequently, Cs is found in only few minerals. Percent amounts of cesium may be found in beryl, Be3Al2SiO36, and avogadrite, KCsBF4, up to 15 weight% Cs2O in the closely related mineral pezotite, CsBe2Li-Al2Si6O18, up to 8.4 weight% Cs2O in the rare mineral londonite, CsK-Al4Be4B-Be12O28, and less in the more widespread rhodosite. The only economically important source mineral for cesium is pollucite, CsAlSi2O6, which is found in a few places around the world in zoned pegmatites and is associated with the more commercially important lithium minerals lepidolite and pedolite. Within the pegmatites, the large grain size and the strong separation of the minerals create high-grade ore for mining. One of the world's most significant and rich sources of the metal is the Tanko mine at Bernick Lake in Manitoba, Canada. The deposits there are estimated to contain 350,000 metric tons of pollucite ore, which represents more than 2/3 of the world's reserve base. Although the stoichiometric content of cesium in pollucite is 42.6%, pure pollucite samples from this deposit contain only about 34% cesium, while the average content is 24 weight%. Commercial pollucite contains over 19% cesium. The Bakita pegmatite deposit in Zimbabwe is mined for its pedolite, but it also contains significant amounts of pollucite. Notable amounts of pollucite are also mined in the Karabib Desert, Namibia. At the present rate of world mine production of 5 to 10 metric tons per year, reserves will last thousands of years. Section 2. Production. The mining of pollucite ore is a selective process and is conducted on a small scale in comparison with most metal mining operations. The ore is crushed, hand-sorted, but not usually concentrated, and then ground. Caesium is then extracted from pollucite mainly by 3 methods: acid digestion, alkaline decomposition, and direct reduction. In the acid digestion, the silicate pollucite rock is dissolved with strong acids such as hydrochloric, HCl, sulfuric, H2SO4, hydrobromic, HBr, or hydrofluoric, HF. With hydrochloric acid, a mixture of soluble chlorides is produced, and the insoluble chloride double salts of caesium are precipitated as caesium antimony chloride, CS4SbCl7, caesium iodine chloride, CS2ICl, or caesium hexachlorocerate, CS2CeCl6. After separation, the pure precipitated double salt is decomposed and pure CsCl is obtained after evaporating the water. The method using sulfuric acid yields the insoluble double salt directly as caesium alum, CsAlSO42 12H2O. The aluminum sulfate in it is converted to the insoluble aluminum oxide by roasting the alum with carbon, and the resulting product is leached with water to yield a CS2SO4 solution. The roasting of pollucite with calcium carbonate and calcium chloride yields insoluble calcium silicates and soluble caesium chloride. Leaching with water or dilute ammonia, NH4OH, yields then a dilute chloride, CsCl, solution. This solution can be evaporated to produce caesium chloride or transformed into caesium alum or caesium carbonate. Albeit not commercially feasible, direct reduction of the ore with potassium, sodium, or calcium in vacuum can produce caesium metal directly. Most of the mined caesium as salts is directly converted into caesium formate, HCOO-CS+, for applications such as oil drilling. To supply the developing market, Cabot Corporation built a production plant in 1997 at the Tanko Mine near Burnock Lake in Manitoba, Canada, with a capacity of 12,000 barrels per year of caesium formate solution. The primary, smaller-scale commercial compounds of caesium are caesium chloride and its nitrate. Alternatively, caesium metal may be obtained from the purified compounds derived from the ore. Caesium chloride, and the other caesium halides as well, can be reduced at 700 to 800 degrees Celsius, 1292 to 1472 degrees Fahrenheit, with calcium or barium, followed by distillation of the caesium metal. In the same way, the aluminate, carbonate, or hydroxide may be reduced by magnesium. The metal can also be isolated by electrolysis of fused caesium cyanide, CsCN. Exceptionally pure and gas-free caesium can be made by the thermal decomposition at 390 degrees Celsius or 734 degrees Fahrenheit of caesium azide, CsN3, which is produced from aqueous caesium sulfate and barium azide. In vacuum applications, caesium dichromate can be reacted with zirconium, forming pure caesium metal without other gaseous products. CS2Cr2O7 plus 2Zr becomes 2Cs plus 2ZrO2 plus Cr2O3. The price of 99.8% pure caesium, metal basis, in 2009 was about $10 per gram, or $280 per ounce, but its compounds are significantly cheaper. Section 3. History. In 1860, Robert Bunsen and Gustav Kirchhoff discovered caesium in the mineral water from Durkheim, Germany. Due to the bright blue lines in its emission spectrum, they chose a name derived from the Latin word caesius, meaning sky blue. Caesium was the first element to be discovered spectroscopically, only 1 year after the invention of the spectroscope by Bunsen and Kirchhoff. To obtain a pure sample of caesium, 44,000 liters, or 9,700 imperial gallons, or 12,000 US gallons, of mineral water had to be evaporated to yield 240 kilograms, or 530 pounds, of concentrated salt solution. The alkaline earth metals were precipitated either as sulfates or oxalates, leaving the alkali metal in the solution. After conversion to the nitrates and extraction with ethanol, a sodium-free mixture was obtained. From this mixture, the lithium was precipitated by ammonium carbonate. Potassium, rubidium, and cesium form insoluble salts with chloroplatinic acid, but these salts show a slight difference in solubility in hot water. Therefore, the less soluble cesium and rubidium hexachloroplatinate, CSRB2 PtCl6, could be obtained by fractional crystallization. After reduction of the hexachloroplatinate with hydrogen, cesium and rubidium could be separated by the difference in solubility of their carbonates in alcohol. The process yielded 9.2 grams, or 0.32 ounces, of rubidium chloride and 7.3 grams, 0.26 ounces, of cesium chloride from the initial 44,000 liters of mineral water. The two scientists used the cesium chloride thus obtained to estimate the atomic weight of the new element at 123.35, compared to the currently accepted one of 132.9. They tried to generate elemental cesium by electrolysis of molten cesium chloride, but instead of a metal, they obtained a blue homogeneous substance which, quote, neither under the naked eye nor under the microscope, end quote, showed the slightest trace of metallic substance. As a result, they assigned it as a subchloride CS2Cl. In reality, the product was probably a colloidal mixture of the metal and cesium chloride. The electrolysis of the aqueous solution of chloride with a mercury anode produced a cesium amalgam which readily decomposed under the aqueous conditions. The pure metal was eventually isolated by the German chemist Carl Sederberg while working on his doctorate with Kekulé and Bunsen. In 1882, he produced cesium metal by electrolyzing cesium cyanide and thus avoiding the problems with the chloride. Historically, the most important use for cesium has been in research and development, primarily in chemical and electrical fields. Very few applications existed for cesium until the 1920s, when it became used in radio vacuum tubes. It had two functions. As a getter, it removed excess oxygen after manufacture, and as a coating on the heated cathode, it increased its electrical conductivity. Cesium did not become recognized as a high-performance industrial metal until the 1950s. Applications of non-radioactive cesium included photoelectric cells, photomultiplier tubes, optical components of infrared spectrophotometers, catalysts for several organic reactions, crystals for scintillation counters, and in magneto-hydrodynamic power generators. Since 1967, the International System of Measurements has based its unit of time, the second, on the properties of cesium. The International System of Units, SI, defines the second as 9,192,631,770 cycles of the radiation, which corresponds to the transition between two hyperfine energy levels of the ground state of the cesium-133 atom. Section 4. Applications. Petroleum exploration. The largest current end use of cesium is in cesium formate-based drilling fluids for the extractive oil industry. Aqueous solutions of cesium formate, HCOO-CS+, made by reacting cesium hydroxide with formic acid, were developed in the mid-1990s for use as oil well drilling and completion fluids. The function of cesium formate as a drilling fluid is to lubricate drill bits, to bring rock cuttings to the surface, and to maintain pressure on the formation during drilling of the well. As completion fluid, which refers to the emplacement of control hardware after drilling but prior to production, is to maintain the pressure. The high density of the cesium formate brine, up to 2.3 grams per cubic centimeter or 19.2 pounds per gallon, coupled with the relatively benign nature of most cesium compounds, reduces the requirement for toxic high-density suspended solids in the drilling fluid, a significant technological, engineering, and environmental advantage. Unlike the components of many other heavy liquids, cesium formate is relatively environment-friendly. The cesium formate brine can be blended with potassium and sodium formates to decrease the density of the fluids down to that of water, 1 gram per cubic centimeter, or 8.3 pounds per gallon. Furthermore, it is biodegradable and reclaimable, and may be recycled, which is important in view of its high cost, about $4,000 per barrel in 2001. Alkali formates are safe to handle and do not damage the producing formation or downhole metals, as their corrosive alternative high-density brines, such as zinc bromide ZnBr2 solutions, sometimes do. They also require less cleanup and disposal costs. Atomic clocks. Caesium-based atomic clocks observe electromagnetic transitions in the hyperfine structure of cesium-133 atoms and use it as a reference point. The first accurate cesium clock was built by Louis Essen in 1955 at the National Physical Laboratory in the UK. Since then, they have been improved repeatedly over the past half-century and form the basis for standards-compliant time and frequency measurements. These clocks measure frequency with an accuracy of 2 to 3 parts in 10 to the 14th power, which would correspond to a time measurement accuracy of 2 nanoseconds per day, or 1 second in 1.4 million years. The latest versions in the United States and France are accurate to 1.7 parts in 10 to the 15th power, which means they would be off by about 4 seconds since the extinction of the dinosaurs 65 million years ago, and has been regarded as, quote, the most accurate realization of a unit that mankind has yet achieved, end quote. Caesium clocks are also used in networks that oversee the timing of cell phone transmissions and the information flow on the internet. Electric power and electronics. Caesium vapor thermionic generators are low-power devices that convert heat energy to electrical energy. In the two-electrode vacuum tube converter, it neutralizes the space charge that builds up near the cathode, and in doing so, it enhances the current flow. Caesium is also important for its photoemissive properties by which light energy is converted to electron flow. It is used in photoelectric cells because cesium-based cathodes, such as the intermetallic compound K2CsSb, have low threshold voltage for emission of electrons. The range of photoemissive devices using cesium include optical character recognition devices, photomultiplier tubes, and video camera tubes. Nevertheless, germanium, rubidium, selenium, silicon, tellurium, and several other elements can substitute cesium in photosensitive materials. Cesium iodide, CSI, and bromide, CSBr, crystals are employed in scintillation counters widely used in mineral exploration and particle physics research, as they are well suited for the detection of gamma and X-ray radiation. Caesium vapor is used in many common magnetometers. The element is also used as an internal standard in spectrophotometry. Like other alkali metals, cesium has a great affinity for oxygen and is used as a getter in vacuum tubes. Other uses of the metal include high-energy lasers, vapor glow lamps, and vapor rectifiers. Centrifugation fluids. Because of their high density, solutions of cesium chloride, CsCl, sulfate, CS2SO4, and trifluoroacetate, CsO2CCF3, are commonly used in molecular biology for density gradient ultracentrifugation. This technology is primarily applied to the isolation of viral particles, subcellular organelles and fractions, and nucleic acids from biological samples. Chemical and medical use. Relatively few chemical applications exist for cesium. Doping with cesium compounds is used to enhance the effectiveness of several metal ion catalysts used in the production of chemicals, such as acrylic acid, anthraquinone, ethylene oxide, methanol, phthalic anhydride, styrene, methyl methacrylate monomers, and various olefins. It is also used in the catalytic conversion of sulfur dioxide into sulfur trioxide in the production of sulfuric acid. Cesium fluoride enjoys niche use in organic chemistry as a base, or as an anhydrous source of fluoride ion. Cesium salts sometimes replace potassium or sodium salts in organic synthesis, such as cyclization, esterification, and polymerization. Nuclear and isotope applications. Cesium-137 is a very common radioisotope used as a gamma emitter in industrial applications. Its advantages include a half-life of roughly 30 years, its availability from the nuclear fuel cycle, and having 137Ba as a stable end product. The high water solubility is a disadvantage, which makes it incompatible with irradiation of food and medical supplies. It has been used in agriculture, cancer treatment, and the sterilization of food, sewage sludge, and surgical equipment. Radioactive isotopes of cesium in radiation devices were used in the medical field to treat certain types of cancer, but emergence of better alternatives and the use of water-soluble cesium chloride in the sources, which would create wide-range contamination, gradually put some of these cesium sources out of use. Cesium-137 has been employed in a variety of industrial measurement gauges, including moisture, density, leveling, and thickness gauges. It has also been used in well logging devices for measuring the electron density of the rock formations, which is analogous to the bulk density of the formations. Isotope 137 has also been used in hydrologic studies analogous to those using tritium. It is produced from detonation of nuclear weapons and emissions from nuclear power plants. With the commencement of nuclear testing around 1945 and continuing through the mid-1980s, Cesium-137 was released into the atmosphere, where it is absorbed readily into solution. Known year-to-year variation within that period allows correlation with soil and sediment layers. Cesium-134, and to a lesser extent Cesium-135, have also been used in hydrology as a measure of cesium output by the nuclear power industry. While they are less prevalent than either Cesium-133 or Cesium-137, these isotopes have the advantage of being produced solely from anthropogenic sources. Other uses. Cesium and mercury were used as a propellant in early ion engines designed for spacecraft propulsion on very long interplanetary or extraplanetary missions. The ionization method was to strip the outer electron from the propellant upon contact with a tungsten electrode that had voltage applied. Concerns about the corrosive action of cesium on spacecraft components have pushed development in the direction of use of inert gas propellants, such as xenon. This is easier to handle in ground-based tests and has less potential to interfere with the spacecraft. Eventually, xenon was used in the experimental spacecraft Deep Space One, launched in 1998. Nevertheless, field emission electric propulsion thrusters, which use a simple system of accelerating liquid metal ions, such as cesium, to create thrust, have been built. Cesium nitrate is used as an oxidizer and pyrotechnic colorant to burn silicon in infrared flares, such as the LUU-19 flare, because it emits much of its light from the near-infrared spectrum. Cesium has been used to reduce the radar signature of exhaust plumes in the SR-71 Blackbird military aircraft. Cesium, along with rubidium, has been added as carbonates to glass because it reduces electrical conductivity and improves stability and durability of fiber optics and night vision devices. Cesium fluoride, or cesium aluminum fluoride, are used in fluxes formulated for the brazing of aluminum alloys that contain magnesium. Prognostications. Magnetohydrodynamic (MHD) power generating systems were researched but failed to gain widespread acceptance. Cesium metal has also been considered as the working fluid in high-temperature Rankine cycle turboelectric generators. Cesium salts have been evaluated as anti-shock reagents to be used following the administration of arsenical drugs. Because of their effect on heart rhythms, however, they are less likely to be used than potassium or rubidium salts. They have also been used to treat epilepsy. Section 5. Health and Safety Hazards. Cesium compounds are rarely encountered by most persons, but most cesium compounds are mildly toxic because of chemical similarity of cesium to potassium. Exposure to large amounts of cesium compounds can cause hyperirritability and spasms, but as such amounts would not ordinarily be encountered in natural sources, cesium is not a major chemical environmental pollutant. The median lethal dose, LD50, value for cesium chloride in mice is 2.3 grams per kilogram, which is comparable to the LD50 values of potassium chloride and sodium chloride. Cesium metal is one of the most reactive elements and is highly explosive when it comes in contact with water. The hydrogen gas produced by the reaction is heated by the thermal energy released at the same time, causing ignition and a violent explosion. This can occur with other alkali metals, but cesium is so potent that this explosive reaction can even be triggered by cold water. The metal is highly pyrophoric, and ignite spontaneously in air to form cesium hydroxide and various oxides. Cesium hydroxide is a very strong base and can rapidly corrode glass. The isotopes 134 and 137, present in the biosphere in small amounts from radiation leaks, represent a radioactivity burden which varies depending on location. Radiocesium does not accumulate in the body as effectively as many other fission products, such as radioiodine and radiostrontium. As with other alkali metals, radiocesium washes out of the body relatively quickly with the sweat and urine. However, radiocesium follows potassium and tends to accumulate in plant tissues, including fruits and vegetables. Accumulation of cesium-137 in lakes has been a high concern after the Chernobyl disaster. Experiments with dogs showed that a single dose of 3,800 microcurie, or 4.1 micrograms of cesium-137 per kilogram, is lethal within 3 weeks. Smaller amounts may cause infertility and cancer. The International Atomic Energy Agency and other sources have warned that radioactive materials, such as cesium-137, could be used in radiological dispersion devices, or dirty bombs.